Hello everyone, in this video we shall start with reactive intermediates. First we shall understand the organic reactions. We all know that the reactants undergo reaction going to give the products. In the detailed reaction scheme, the substrate reacts with another substrate or the reagents in presence of catalyst in the medium, that is in the solvent medium. We are going to get the products and also byproducts. Okay, this is the organic reactions. When you study the detailed detailed steps of this reaction, means the electron movement and the bond cleavage, new bond formation, and the rate of the reactions is called as the reaction mechanism. The study of the each step describing details of electron movement and the bond cleavage, bond formation, and the rate of the transformation of reactants into products is called as reaction mechanism. Okay. Then what actually happens in the reaction, in the organic reaction, is you know that there will be two steps. Means when the substrate in the presence of catalyst, there is a cleavage of the bond, means there is a fission of a bond takes place. And let's take an example. Here we have this substrate. This is the example. This is a molecule. This is a substrate. These are the atoms. Let's consider these are atoms. This is a covalent bond. And in the first step, these two will means this substrate. This is the whole molecule. This substrate will, in the presence of catalyst, the cleavage of bond takes place. Means the bond breakage of the bond takes place. Here the bond breaks, so that you are going to get the unstable species. That unstable species is called as intermediate. Okay, let's consider here the bond breakage takes place. You are going to get the separate species A and B separate species. These are called as intermediates. Means this is called as intermediate. This intermediate is reacts with the another reactant or the reagent. Here the bond formation takes place. Let's take here the nucleophile. This is a general reaction or then example. This intermediate is reacts with this another reactant. Here the bond formation takes place in between this another reactant and the intermediate, and you are going to get this type of product. So that this is called a reaction. There are two steps. Substrate first undergo the bond cleavage in the presence of catalyst. You are going to get the unstable species, highly reactive unstable species. This will react with the another reactant. Here the bond formation takes place between this reactant and this intermediate, and you are going to get this product. Let's view at the energy profile diagram. This is the starting material. This may be AB. Okay, this is first step. In the first step, the bond cleavage takes place. Here the bond cleavage takes place. This is transition state 1. This is the first transition state. And here when the energy decreases, in the first transition state energy is high, and when the energy is low, this is called as intermediate. This is intermediate stage. Here this is first stage, this is second stage. Second stage is the intermediate stage, and here the intermediate reacts with another reactant. Again the energy increase, and there is a new bond formation between this intermediate and the nucleophile takes place. That is called as transition state 2. And here the bond formation takes place in the transition state, and the product formation takes place. Here the product formation takes place. Here the product, as in the example, here the product formation takes place. This is the energy profile diagram of the reaction. So in this video we are going to discuss about these intermediates. These are intermediates are the highly reactive unstable species. So these will determine the rate of the reactions. Means if the intermediates are highly stable, then the intermediates will easily form. Then that will easily react with the nucleophile or the another reactant going to give the product. When the intermediates are highly stable, then the formation of these intermediates will be faster. Then it can easily react with another reactant going to give the product. If these intermediates are less stable, then this intermediate formation is weak, so that the reaction will be rate of the reaction will be less. Okay, so that now we shall discuss about these intermediates. There are, as you know, there are the carbocations, carbanions, free radicals, carbenes, nitrines, benzenes, and ylides. Okay, these are the common intermediates you can find in the organic reactions. Okay, let's discuss about the intermediates. Before going to the intermediates, we shall understand this fission of a bond, means bond cleavage, how the bond cleavage takes place, what are the types of bond cleavages. So then only we can determine the which type of intermediate will form when there is a different type of fissions will takes place. Okay, the formation of the intermediates is also depends upon the fission of a bond. Okay, so let's begin with the fission of a bond. Here we know that the fission of a covalent bond, we know that the carbon having 4 free electrons in the outermost orbital, so that it can, the valence of carbon is 4, it can make the 4 bonds with the other atoms. By covalent bond is a sharing of electron pairs. You know that this carbon is sharing its 1 electron in this hydrogen, and these both are sharing these 2 electrons. Here also this is carbon is sharing 1 electron, hydrogen is sharing 1 electron, hence there is a new covalent bond between this carbon and hydrogen. Here also same, so that its octet is complete, these hydrogen's octet is also complete, hence this methane is formed. Here we know that there are 2 electrons, one is belongs to carbon and another is from hydrogen. These 2 belongs to both the carbon and hydrogen now. Okay, so fission of a bond means the cleavage, means the break of this bond. How there are 2 types of fission takes place. There are 2 types of fissions are there. One is homolytic fission, another one is heterolytic fission. In the homolytic fission, fission of a bond takes place homolytically, means fission means break of this bond takes place, and one electron goes to one atom, another electron goes to another atom. Means the after the cleavage, the electrons shares equally. Here you can see that one electron goes to this A and atom, another goes to B atom, so that here you got the A free radical and B free radical. This is called as homolytic fission. This arrow is called as Fishhook arrow, and this shows the movement of single electron. In the homolytic fission, one electron goes to one atom, another electron goes to another atom, means the cleavage takes place equally. The shares, after the cleavage, the electrons equally shares between the 2 atoms. Let's take an example. This is methyl chloride in the presence of sunlight. After this cleavage, one electron goes to this methyl carbon, another electron goes to this chlorine, means chloride, so that we are going to get the chloride free radical and methyl free radical. So these type of intermediates, these are the intermediates. These type of intermediates are formed in the homolytic fission. Okay, then in the next one, that is heterolytic fission. Heterolytic fission means fission or the cleavage of a bond takes place, and the after the cleavage, electrons shares heterolytically, means after the cleavage, both the electron goes to only one atom, which is more electron negative, more electron negative out of A and B. B is considered B is more electronegative, so that both the electron goes to B, so that A gets the positive charge and B gets the negative charge. This type of fission, in which both the electrons which are there in the covalent bond between atom A and atom B, after the cleavage goes to only the more highly negative out of or the more negative or more electronegative atom, so that this type of fission is called as, consider this is a heterolytic fission and this is homolytic fission. Let's take an example. This is methyl bromide. When the methyl bromide undergo heterolytic fission, bromine Br is more electronegative, so that both the electron goes to Br. When you heat this, Br gets both the electrons, so that this methyl CH3 gets the positive charge and Br gets the negative charge. This is called as carbocation. Okay, this type of free radicals you can carbocation, carbanions you can get in the heterolytic fission. So this is homolytic fission and heterolytic fission. So these fissions will decide which type of free radicals will form. Okay. Let's take another example for carbanion. Let's take, this is CH3 Z. Here we will take this Z as a this is more electro positive than the carbon, so that here out of these 2, carbon is more electronegative. So that both the electron goes to this carbon, not this Z, because this is less electronegative than carbon. Hence carbon gets a negative charge. Hence it is CH3 negative plus Z plus. So that here it is carbanion. Here it is CH3 plus is carbocation, CH3 negative is carbanion. Okay, these type of intermediates will form in the heterolytic fission or heterolytic cleavage. Okay, let's start with the carbocation. It is also called as carbonium ion. It is also called as carbonium ion. We all know that CS3, here I will take an example of CS3Br. CS3Br, you know that carbon is sp3 hybridized here and this is tetrahedral structure. The structure of this CS3Br is tetrahedral. When this Br undergo heterolytic fission, Br is electronegative, so both the electron goes to Br. Hence the carbon gets positive charge. This is called as carbonium ion or carbocation. This is the intermediate. Because Br is more electronegative than carbon, both the electron goes to Br because of the heterolytic fission. Hence carbon gets the positive charge. This is called as carbocation. This is the intermediate. Let's discuss about the structure of this carbocation. Here now it is electron deficient. As you know that both the electron goes to Br, hence it is electron deficient, so that it gets a positive charge. And this is sp2 hybridized now. The CH3 plus is a carbocation is a sp2 hybridized. The structure is trigonal planar shape. It is having trigonal planar shape. It is having vacant p orbital. It is having vacant p orbital, having positive charge because it is electron deficient species, and it is carbon is sp2 hybridized carbon. Okay, and then these are the points. We can find these carbocations in the polar covalent bonds. Hence only means here this is called a polar covalent because Br is more electronegative than carbon. Hence both the electron goes to Br. This type of bonds are called as polar covalent bonds. And this is undergo heterolytic cleavage. Carbocations are formed in the heterolytic cleavage, and after this cleavage, this species is electron deficient, and primary requirement for this carbocation is plenarity. Plenarity is the primary requirement for the carbocation. You should remember this because when you have the plenarity, then only it is stable. If it is non-planar, then the carbocation will not form and it is highly unstable. So that the carbocation, the carbon should be planar. Okay, let's discuss about the stability of the carbocation. In the introduction, we have discussed that the stability of the carbocation or the intermediates is very important because when the stability is high, means if the carbocations are more stable, then the easily formation of carbocation takes place. Okay, if these are more stable, then the formation of carbocations is easily takes place, means it is more stable. Then only it can react with nucleophile easily, so that reaction will be faster. Okay, if it is less stable, if the carbocations are less stable, the formation will be slow. If the formation is slow, then the reaction will be slow because it cannot easily form and it cannot react easily with the nucleophile or the other reagent, so that the reaction will be slower when it is less stable. Okay, 2 points are very important. And then we all know that the carbocation is electron deficient. So when it will be more stable, out of these two tertiary carbocation, it is secondary, it is primary, and it is methyl carbocation. Here we know that the R groups are electron donating groups. Here we have 2 R groups, here we have 1 R group, and there is no R group. R group is electron donating group. We already know that carbocation is electron deficient. When the carbocation is having 3 R groups and these R groups are donating electron, so that when these 3 groups are donating electron, it will be more stable. So the formation of this carbocation, means the tertiary carbocation, is easily formation takes place, hence it is highly stable than this one because there are 2 R groups are donating electrons to carbon. Because this is carbocation is electron deficient, when there are the R groups are supplying electrons to carbocation, it will be stable. So then this is stable than this because only R is attached. There is no R, hence it is less stable than this. This is less stable than this. This is less stable than this. Okay, this carbocation is electron deficient. When you supply this with the electron donating groups, then it will be stable. Okay, tertiary carbocation highly stable than the secondary, than the primary carbocation, then the methyl carbocation. Okay, let's discuss more about the stability of carbocations. The order of preference of effects on the stability of carbocations is resonance is more effective than hyperconjugation effect than the inductive effect. If in the molecule you can find the resonance structures, means if there is a resonance, the carbocation is resonance stabilized, then that is more stable than the hyperconjugation. If the hyperconjugation is more, then that will be more stable than the inductive, where you can find the inductive effect. Okay, let's discuss about the examples. Here this molecule is highly stable because this is tricyclopropyl methyl carbocation. This can show the dancing resonance, means in the resonance this bond breaks and this there will be a new bond between this carbon and this carbon. This bond breaks and there will be new bond between this carbon and this carbon, hence this shifts here. Okay, like that the carbocation shifts takes place, hence this is tricyclopropyl methyl carbocation. This is highly stable. This shows the dancing resonance, hence this is highly stable than the other molecules. And the next one is this is trophylium cation. This is more stable than even the resonance structures. This can show the resonance. This carbocation, this is methyl carbocation having 3 phenyl groups, means triphenyl methyl carbocation. This is less stable than this trophylium cation because of this carbocation, this molecule is getting aromaticity, so that it is more stable than even the resonance structures. This tropylium cation is more stable because of this carbocation, this trophylium cation is getting stable, means it is getting aromatic character, so that it is more stable than the resonating structures, means resonance structures. Here we have this methyl carbocation having three phenyl groups, so that there is a more resonance, hence this is more stable than the methyl carbocation having 2 phenyl groups. This is diphenyl methyl carbocation because the resonance is more here than here. Then next one is here you can find the both inductive as well as hyperconjugation effects. Hyperconjugation means you can find 3 3 3, so totally you can find 9 hyperconjugation structures for this is tertiary butyl carbocation. You can find 9 hyperconjugation structures for this tertiary butyl carbocation. Hence with the hyperconjugation can also show the inductive effects, and this is more stable than this compound which showing the resonance structure. This is more stable than the allyl carbocation. Here you can find the resonance. This is more stable than this allyl carbocation, and this allyl carbocation. These are almost same, but this is a little more stable carbocation. Here we have allylic carbocation, you have resonance, hence this is highly stable. This is more stable than this isopropyl carbocation. Here you can have 6 hyperconjugation structures and also 2 methyl groups having inductive effect. Both we are having both hyperconjugation as well as inductive effect. This is more stable than this one. Here also we have inductive effect as well as the hyperconjugation effect, but the hyperconjugation less here than this isopropyl carbocation, so that ethyl carbocation is less stable than this isopropyl, and this is less stable than this methyl. This is highly stable than this methyl carbocation here, because there is no inductive effect and there is no hyperconjugation effect, hence this is less stable than this ethyl carbocation. And the next one is this. Okay, this is less stable than this methyl carbocation, because the primary requirement for this uh, formation of carbocation is planarity. Planarity is the primary requirement, because here there is no planar. This carbocation is not planar, hence this is unstable. The formation of this is highly unstable. There is no means it is highly unstable, so there is no formation of this type of carbocations because there is no planarity, hence this is highly unstable. That this is means this structure is less stable than this one, because here we know that this is anti-aromatic. Due to this is anti-aromatic. This carbocation is anti-aromatic, so that is highly unstable. This is highly unstable because this is anti-aromatic. So this is because of this positive, this carbocation gets the stability and gets the aromaticity, so that it is stable, highly stable. Because of this carbocation, this is unstable, hence this is anti-aromatic, hence it is highly unstable. Okay, this is the stability of carbocations. You should also know the some of the reactions which can have these carbocations as intermediates in their mechanism. Okay, here I will mention some of the reactions, named reactions, which can have the carbocation as the intermediates. Okay, Friedel-Crafts reactions, these are the important reactions. Friedel-Crafts reaction, here you can see that this generates the carbocation as the intermediate. This is carbocation intermediate. And next one is Baeyer-Villiger oxidation. In the Baeyer-Villiger oxidation also we can find the carbocation as the intermediate. And this is Dakin reaction. This is the mechanism is same as Baeyer-Villiger oxidation. Here also we can find the carbocation as the intermediate. And another named reaction, that is Beckmann rearrangement. Here also you can find the carbocation as the intermediate. And another rearrangement, that is pinacol-pinacolone rearrangement. This is also having carbocation as the intermediate in this rearrangement. These are the some of the important reactions, named reactions, which can find the carbocation as the intermediate in their mechanism. In the exams, they can give you the some of the reactions, and you should find out which reaction can have the intermediate as carbocation, means in which reaction the intermediate will be the carbocation. So that because of that you should know the which reaction can generate the carbocation intermediate. Okay, thank you.